So I'm in between jobs, so I have tons of free time, which is fun. So I mostly used to do computational physics. I switched to ML maybe, I guess, 8 years ago or so. I did a bit of theorem proving, so I did some work in Google Brain on theorem proving ages ago, but then since then I've been working on AI and AGI safety. And this is like, I think maybe the right thing I should be doing is sort of important-wise. There's unsatisfying aspects of it. It's like everything is mush and sort of uncertainty and messiness. So it's nice to do hobbies where things are true. So that's the advantage of this. I'll mostly talk about the Mandelbrot set proof. So the Mandelbrot set is connected. We have that formalized in Lean 4. I have done some formalization of interval arithmetic. So this picture is from Lean, and every pixel is correct. It's a point sample, I'll get into that a bit, so not perfectly correct. And then I did a bit of work around AI safety, sort of a complexity theory proof that's related to AI safety. And I'll only briefly touch on that because that requires lots of background. The main caveat is that this picture is Lean. This picture is Python and JAX and the GPU, because it's much faster to prepare a talk if you have a GPU. So the rough sketch of the proof that this set is connected, the black set, is that we first look at it as part of the sphere. It's more natural that way. And then so the outside of that set is a disk after some analytic bijection. And so we construct this set explicitly, sort of this function explicitly that maps between the exterior and the ball, and that immediately shows that the thing is connected as sort of an easy corollary. So the work is mainly sort of constructing this function. This is kind of the standard proof, and also the nice thing, there are kind of simpler topological proofs that you could do in kind of with less kind of machinery set up. But then I think if you wanted to continue towards more kind of complex dynamics or do other things, it's nice to have the function. So I sort of did it the old canonical way. So the rough setting is we have some space of functions f sub c, so they're parameterized, sort of a one-dimensional function from sort of c to c, parameterized by c. So that the state variable is z here. Apologies for that. We're going to iterate this a bunch of times and then study the kind of evolution of that function. So the picture you should have is there's some 2 complex dimension, 4 real dimensional manifold, where this dimension is sort of the parameter space, so where we are in our iteration around. And then this dimension is, this dimension is dynamical space, and then this C dimension is parameter space. So that's kind of what function we are iterating, and we'll study how things vary. And then the picture is that the Mandelbrot set sort of exists in parameter space, and the Julia sets exist in dynamical space, and most of the work happens in dynamical space. And then at the very end, you sort of lift it to parameter space. This is actually what the Mandelbrot set looks like. That other picture is kind of confusing and misleading. So this is the view from infinity if you invert. So right in the center of that is infinity, and then near 0 there's a Mandelbrot set. So like at the outside of the infinity view is the Mandelbrot set. And then the iteration near infinity looks like squaring, sort of almost like squaring. So z squared plus c kind of turns into, if you invert, roughly w squared plus some higher order correction. This higher order correction is annoying, so it'd be nice if we could just exactly turn our iteration near infinity into just squaring. So it's roughly there, and then it turns out the mapping that will do this simplification of the exterior is the mapping that converts the iteration from squaring plus some nonlinear term into exact squaring. So near infinity, there's some nice infinite product formula, which is given here. So here again, we have f, which takes a parameter and a state and gives you a new state. And then we're going to compute some function b, which takes a parameter and a state and warps the state so that our function iteration is just squaring. And so again, near infinity, we have a nice infinite product. The problem with this product is that you have to raise to some fractional power. So if you're sort of far enough towards infinity, that power is just around, it's some power of a complex number that's near 1, so it has some simple properties. If you get too far away, then the power kind of explodes and there's branch cuts and so on, and that's kind of the fundamental block. So again, if you can take this power and you can formalize that in Lie kind of near infinity, it's fairly simple. As you go further away, you don't know which branch cut to use, so you have to kind of choose that arbitrarily, and that kind of reflects the actual dynamics. So we'll get to that later. But the absolute value is fine, so that is independent of the branch cut. So we can write down the potential function, which is the absolute value of kind of this infinite product, sort of near infinity, and then it obeys a similar equation to the kind of the full coordinates. So we can immediately kind of explode that throughout the whole manifold. So that kind of suddenly exists kind of everywhere in space. Just by sort of, all we do is we take a point, kind of iterate it until we get close to infinity, and then kind of pull that back to the local point using a bunch of square roots. Okay, so let's see what that looks like. So this is sort of the picture if you hold C fixed. So again, the Mandelbrot set in the middle here is the picture of all of the Julia sets kind of for varying C. If we fix C, we fix one function that we're going to iterate. Out slightly inside the Mandelbrot set, you get a Julia set that is connected. And it turns out for those, you can extend your kind of nice coordinates all the way to the boundary. That's great. If you're slightly outside the Mandelbrot set, you get a totally disconnected. So this works as long as we don't hit a value of the potential, which is a pre-image of a critical point of your function. So basically, if none of the iterates of this function ever go critical, then you can always continue locally, and then it turns out you can continue globally as well. And so this works kind of as far as that goes. At this point, basically the level sets have like sort of two level sets have kind of wrapped around some part of the Julia set, and they collide, and at that point, sort of things explode, and you have to do something else. So that part gets hard, but we don't need it at all. So we can do this continuation kind of just with kind of simple analytic continuation. Everything is kind of single valued and clean on some manifold. We sort of, before we hit that point, we've already proven connectedness.
Because this is like outside of the random settlement.
So I don't actually understand at an intuitive level why, although I can give you the argument. Here's the argument. So you need to avoid a pre-image of a critical point. Z squared plus Z has one critical point at Z equals 0. The function you need to remap the exterior of the Mandelbrot set is the diagonal map of your coordinates. So it's B, C, C, basically. And CC is the image of the critical point, because it's what you get if you apply your function to 0. Mm-hmm. Therefore, its potential is smaller, because you've kind of iterated one step further. And therefore, it can't be the pre-image of any other critical points, because there are no more. You kind of walked further closer to infinity than the only one. So you're done. I don't know why this is true at a deeper level than that. I think it isn't true in kind of, if you want to do other things, there are other areas where it's kind of not. Like, this is only true for the Mandelbrot set and not for, say, a general class of functions. So for the Mandelbrot set alone, like, you only need to go to like right up until the point where this kind of explodes, and then you can stop. This is not enough for like the kind of heavier results in complex dynamics. So if you like, one of the major results is that you can every kind of ray down from infinity towards the Mandelbrot set with a rational angle, like a rational equals 2 pi lands. That result requires you to continue all the way to the boundary, and then you have to deal with the multi-valueness in a meaningful way. So that's kind of the structure of the proof. I think the sort of mapping this to Lie, like most of the work is of just a bunch of kind of continuous induction principles applied over and over again. So you're sort of growing these rays, kind of proving that kind of injectivity kind of flows outwards from infinity, that kind of thing. Here are the kind of the two big examples. First one. It took me ages to write down kind of the induction hypothesis for growing these rays. Sort of tried. You can kind of express it using either the coordinates or the inverse of the coordinates, or you can express it for like a single direction or a whole circle of directions, or in a neighborhood. And I kind of tried all these variants. I finally found this one. So that like took a bunch of the time, just like me stumbling around in kind of hypothesis space to find this one. But this one works. And so basically you have your coordinates are going to live kind of, they're going to map from the parameter space times the manifolds to complex numbers. And the rays go the other way. So they map from parameter space times complex numbers to the manifold. So these rays are in green. They sort of expand out from infinity and are sort of parallel to the potential level sets, as you'd expect. And then you can just sort of prove that, well, the set of distances to which you can extend these rays is open and closed, and therefore it goes all the way to the end, which is straightforward once you get the right hypothesis. These are pretty. It's funny. So I haven't written any of these. Like I had these pictures in my head doing all this work, staring at lean text, and so getting to write the talk was fun. Because I actually got to see what they were, which was nice.
How did you make all the cool graphics?
It's just JAX and Python. I have a collab. It's linked in the talk. But the Mandelbrot set is very easy to visualize because you can just compute stuff. These rays are kind of traced by like the site that being solver. It's all fairly straightforward. I have the code to share. Another fun case is if you continued these rays out to say radii less than p, and you want to show that they snap all the way to radius equal to p, then what could happen is that as you approach the boundary, you have this kind of topology sine curve thing where it goes like haywire and kind of like limits out of some messy set. But you know that set is connected because it's the ends of a ray have to be connected, and you know it's totally disconnected because the only answers are given by the branch of CPAL that you picked when you're sort of like taking the infinite product, basically. And something that's connected and totally disconnected is a single point. You're done. Show that it converges. It's simple but fun. Another example of like induction is kind of proving that you get an injected map here. So you want to show that in the Mandelbrot set, say no two rays kind of come out and then ever collide. And you basically do that by descent. So you take some kind of intersection, you assume they collide, and you can kind of push that back towards infinity, towards like the start of the rays. And there are two cases. So if the intersection is like far apart, so you have like rays that are colliding like this, then you can just kind of walk along them basically by the open mapping theorem. And then the other case is where you have a collision like this. So you have these counterexamples, and as they kind of approach each other, they converge through the same point. And so you have to show that once they hit at the same point, you can push that into different points kind of further on. And that also uses Bottcher coordinates. So if you have an analytic function and it has derivative 0, so you have these colliding kind of injectivity failures, near a 0 of an analytic function, every nearby point is assumed at least 2 times, and you can explicitly construct the space warp that rotates around the point that sends kind of matching functions to matching functions. And that lets you like push the counterexample down to lower potential and kind of keep it going towards infinity. So I started this, I think, the fall before kind of maybe the beginning of the Lean 3 push. So there was a fair amount of kind of missing basics around analytic functions and then analytic manifolds. Those are still mostly missing. So like Osgood's theorem was missing, Hartogs theorem, which is like a fancy version of that with no fewer assumptions missing. The basic fact that like uniform limits of analytic functions are analytic. I think that's still missing. So I need that. I'm not sure. Yeah, that's fine. It's very easy to prove.
I am pretty sure there's a PR.
Anyways, so there's a bunch of, there's a bunch of machinery I had to set up. So this is all kind of along the way. The open-epic theorem existed, but not the version where you parameterize it by C basically. So you have to like move it to that. And then of course that's not a manifold and so on. I think some of this is my ignorance, but manifolds have a ton of are like just painful to work with because you have all these charts and you have to like make sure you don't leave the charts all the time. That's kind of a nightmare. Some of that is again my lack of knowledge of tactics. And then kind of missing automation. So the two big ones for me are inequalities. So I think there's some, I have one more that does kind of like, bunch of overlapping, kind of just a bit more than current stuff, and a bit less than kind of some messy Venn diagram. And then I think eventually you want kind of more high power support for like polynomials and nonlinear polynomials and stuff like that. But that's probably like a ways out. And then I think the other thing is that there's much better support, say, for things that are true everywhere than things that are true in patches of patches. And you have two choices. You either work in a subtype, and that's just has its own kind of own pain points, or you have continuity on or analytic on or the like. And then you have this mixture of kind of structural assumptions and inequalities and so on. And that support is not really there.
Question: do you use continuity on for like open sets, or do you use them for any type of sets?
General sets.
General sets.
Mostly open sets, but often general sets. I also use analytic on for well, I use that for a bunch of closed sets, but they do extend. And then this is maybe again my lack of mathematical, but this is a ton of just horrendous calculations. So like if you do z to the d, this is like the place 2d with 2, right? Z to the d plus c, that changes log z by roughly log d. This is like how fast things escape to infinity. And it's like there's a bunch of horrendous calculations and bounds and stuff to get that result. I don't know how to simplify that, but it's a mess. And then it is very satisfying. This is of course obvious, but that's all analytic manifolds and this mess. In the end, you can just write down what the manifold set is with no dependencies at all, and then write the theorem that it's connected. And you like rewrite it to your general stuff and like prove this. Questions about that, and then I'll go to.
Yeah, maybe I should just add about the connected on continuous on. That means you don't get to have the fact if you're continuous on S and continuous on T, then you're continuous on S, V, and T. Because that only works for open sets. So
right, that's
what do you expect from like continuous on that?
I mostly wanted to do all of the work that is like the structural work, and then leave me the hypotheses that are like, okay, like there's, say, I typically have something like, well, let me just go back to this.
Let's say if I give you like x log x.
So here's this infinite product, right?
Yeah.
So you imagine that like you have a bunch of expressions that involve like say powers and f, and you want to say continuity on, and in that tree you're going to have f is continuous on this set, and c power is continuous away from the negative real axis. And you basically have hypotheses for those.
Yeah.
And so I can either do them myself once continuity does the rest, or I can give them as hypotheses at the beginning in my closing tactic form. But either case, there's a bunch of annoying work, which is just apply like c power continuous, apply continuous on comp, all of that stuff, and that's not fun. So that just means that you still have to do the work manually to do the final kind of the core things like f and g and c power again away from.
Okay, but like if I give you something like if I give you something like x log x, would you expect it to like prove continuity everywhere I set that 0?
Well, that isn't continuous.
X log x.
Oh, you mean sorry, the real one? Yes.
Yeah, the real one. The real one. Sorry, I wasn't. Yeah.
I'm sorry. I've been living it. So I. Yes.
Yeah.
Well, either that or you get a hypothesis at the end. You get a goal at the end, which is like x times 2.
Yeah. Okay. I think that's hard.
Yeah. I don't disagree. Okay. So I like numerics, so I've done a bunch of like numerical simulation. Numbers are fun. I like using computers. So it's fun to mix heavy computation and theory, and useful at times. There's not much support for this currently in math, so you can't like for various reasons some of the theory at the end requires actual numbers, and like x with a number is kind of pulling teeth. You can do it. It's just like it's not very well supported. But if you wanted to do x plus like x with 1 plus, like there's just like simple evaluation of simple formulas is not really good. Getting kind of tight down to them, it's not automated. And then if you want to do fancier things like render the Mandelbrot set or bound its area, you want numbers. The nice thing would be actually to use double persistent float, but this is not great for verification. You can make it work, but you have to trust IEEE. And if you want to do nice rounding, there's annoying compiler things that make it hard. I'll skip that stuff. So I'm going to do something way slower than that. So my floating point type is a whole 64 bits of precision, like n, and then whole 64 bits of exponent, which is basically corresponds to n times n times 2 to the s minus 2 to the 63, just to keep the exponent positive. And then it's dependent type, so it also knows a bunch of things about its kind of normalization form. And then the interval is just kind of a lower bound and an upper bound. And the guarantee that you'll use in practice is that the true answer is in between those bounds. And the interval knows that it's not empty. It knows that low is less than or equal to high. There's also nans. So anything can become nan, which means whatever, like it's some number could be in it. And then there's a bunch of type classes for one type approximates another type. So the two main things are interval approximates reals, and box, which is poorly named, approximates complex numbers. And that means that there's some map from intervals to sets of reals, which happens to be either infinity or a finite closed interval. And then a whole bunch of type classes for addition is conservative, so it respects like the addition in the conservative in the approximate type respects addition in the real type, and that's true for all the field operations and so on. So I have like enough formalized to render the Mandelbrot set. So that's all of the ring operations on floating point numbers, and then other details, adds, so on. All of the field operations on kind of interval and box, so you can do division and so on, using Newton's method. And then in order to do kind of pullbacks of the potential function, you need exponentiation. So x log powers for those are kind of Taylor series. Doing things in fixed precision, like 64 bits, in hindsight, it's not clear this is the right answer. It meant that like, I think eventually this means that it will compile to kind of unboxed types once they get the new code generator. It's not yet. But it means that every time you're doing a theorem, you have to worry about overflow across the 64 bits, which is just lots of pain. So it's way harder to set up, and also like just with this finite precision, and then also going to floating point means you have to worry about kind of denormal numbers and other kinds of overflow and all this kind of mess. But floating point is way easier to use. So I actually first wrote most of this with fixed point, where like there was a type fixed s, where s was like a varying position at the decimal point or the binary point. And then I kept trying to use it, and every downstream bit of code has to worry about exactly where the scale is, and it was just sort of a nightmare. And then I kind of rewrote everything in floating point, which was painful but better. And then dependent types. So as I mentioned before, like both the floating point type and the interval type know various invariants, and that's quite useful because every downstream method becomes kind of that much simpler. Like the floating point ordering on the floating type respects the real number type, real number ordering exactly, which is convenient, unless you're nan, which is great. Yeah, actually, even if you're nan, because nan has to be the maps to the lowest buffering value. So that was like hard to set up, but then I think it's quite nice to use, except that it's not so fast. And then I think once you have all these sort of lemmas that in arithmetic or calculations in the approximate type approximate the real type, then you can register them all with some tactic. I did mono, but I think mono is probably the wrong choice. Let's just have another tactic. And then in practice, you basically can kind of, you want to prove that some approximate calculation matches some real calculation. You can kind of rewrite the real the calculations to match structurally, and then just dispatch, like mono just dispatches that these, like anything that matches structurally and started out matching matches at the end, which is quite nice.
Is this not like mono views? Is mono supposed to be to deal with this kind?
This is, I think mathematically it is very similar to mono.
Yeah.
But I would say it is mono views, and I wouldn't upstream this. I would upstream it as an asap rule set. Did you raise your hand, or is that it?
No.
In this case, by the way, so I think there is some definition of real powers and negative numbers, but I happen to make the conservative one just explode to nan for negative numbers. So the second branch in this proof is if it's negative, the result is nan. The approximation set for nan is univ, so you're done generally. And then it's satisfying to do unit tests. So here's the unit test for the exponential. I've already proven that the exponential is conservative, but there's no proof at all that the intervals you get out are remotely tight. So they could just be enormous all the time. So the unit tests are just computing some exponentials and checking that the size of the interval is small, and not that the position of the interval is anything meaningful at all, which is guaranteed by the derivation.
Wait, sorry, is that what's that notation?
Which notation?
1e3 minus 18. Did you?
That's not my notation.
It's not the notation. This is.
No, that's scientific. Yeah, of scientific.
Ah.
It's quite useful.
I literally never seen it.
I have more of that in the future slides. Actually, it does come up. So it basically turns into a nat and a shift, and there's like 3 numbers for some reason. I forget why. But yeah, you can any type can be registered as scientific. Okay, so here's a Mandelbrot render. This one is formally verified point sample, so we'll get to that in a second. This picture is so the potential function is smooth everywhere in space. It's 0 at infinity. It kind of smoothly rises towards 1, and then it's exactly 1 on the Mandelbrot set. It's real analytic off the Mandelbrot set, and then it's just hard 1 inside the set. So it's continuous, so that you can actually do like you can smoothly approximate it everywhere in some guaranteed way. But this is not the perfect thing, because if you imagine each pixel is a square, I'm not proving that the color is correct throughout the square, just at the center of the square, which is unsatisfying. I will fix that later. And then the fun thing is that, again, there's no theorem, and there can't be a theorem that that the intervals are very tight. That would be extremely hard to write down. So this has red pixels, which indicate that there was some explosion. Basically, the guarantee, either you hit nan, or the guarantee that you're within 1 kind of 256 color value of the true answer is not satisfied. So it just produces a red pixel. This is a very high resolution image, so you can like zoom way in, and there are the red pixels. There are a few of them.
Question. Yeah. Can you not eliminate those red pixels using the fact that it's connected? The Mandelbrot is connected.
You can do that, yes. That requires you to do more data structures. So that's one. It's also like the reason those red pixels occur is actually there's a fundamental reason, which is like fixable. So those can go up and do some more work. So if you take a point-like interval and you iterate it with your z² plus c function, every time you do that, the interval gets roughly twice as large plus some extra factor. So it's exponentially growing. And then there's one of basically like two things can happen. One is you actually escape to infinity, and then you're really big, and then the potential function will be small, and you're done. You're going to get a good estimate. The other is you stay close, and you actually say you converge, so your interval forever stays small because it's actually there's a contraction happen, which is like yanking you towards the point, or you're near the boundary, in which case what happens is the interval keeps growing, gets bigger and bigger, but because it's near the boundary, it has to contain a Mandelbrot set, and so your interval goes in every direction, and at that point you kind of have to just throw up your hands and walk back a ways and say where in the iteration was my best estimate of the value, and I don't do that kind of iteration operation.
So compared to your previous picture, that one looks relatively blurry, or there's not that
Yeah.
very crisp boundary.
Okay, so here's the slide answering your question.
Okay.
So this is the same picture as before, but so this picture here is using two completely different techniques to compute blue pixels. One technique is, so you iterate for a while. If you escape towards infinity, then I have this sort of thing on the top is a bound, basically potential is roughly 1 over c absolute value near infinity. And the fall off is nice, almost quadratic, not quite, fortunately. So that bound gives you the smooth fall off. That's the thing that's falling off towards clear in this case. And then if you don't escape, there's another bound from theory that within the disk of radius 4, the potential is no bigger than 0.216. Unscientific. So if you color those two pixels different colors, you get this picture, which is what people always draw.
Okay.
So this is the picture, and it's way cooler. It's a much nicer picture. But who knows whether those black pixels are actually black or they're blue? Because there's it could just be you iterate more, you would escape, and then they would be blue, and that's unsatisfying. It's unsatisfactoriness there. If you want to go further than that, you need this. Well, you need two things. So I'll just say this first. So if you're inside the Mandelbrot set, there are two things that can happen. One is you stay chaotic forever. So you just do something crazy and non-repeating indefinitely. That's what happens at the boundary. Conjectural. I think it's, anyways, probably. And then if you're in a hyperbolic component, you converge at least exponentially fast to a fixed point, or fixed or repeating cycle rather. And you can detect that that convergence numerically and prove that you're inside. So I will write that eventually, but that's future work. So the other thing is that, as I said, you have a square. It's unsatisfying to say I've formally computed the value at the center of the square. You want to say what's the whole square look like? And for that, this is not a new technique, but no one has done it in Lean yet. If you evaluate both the potential function and its derivative at a point, then you know basically for if you have a small derivative, you have a large disk, like a circular disk, where you know the bound. Mm-hmm. Basically because you know the function is injective. The Bottcher coordinate is not the potential function. Those are injective. So it can't kind of break too fast. It can't go non-injective too fast. So, but prove this theorem, which is not that hard, but I'm working on it right now. Then you can do a point sample in the middle of a pixel, and then also get the derivative of the point sample, and then you get some theory estimate of the surrounding thing using the fact that the coordinates are injective. So it's a heavy theory plus numerics, which is fun. This is hard because the Kobe-Korda theorem, you kind of want to do things like what's the area within some horrible parameterized disk, and Lean is missing most of that stuff. So there's no Jordan curve theorem, no not very much kind of area parameterization. So I have to do things that are basically what I have to do is you have some horrible thing like this. You want to get the area within it. So you zoom out towards infinity until it becomes star-shaped. And then you're well, this one I can do. And then you can just port it back in to the but that's a whole bunch of extra work which you would not do in pen and paper. And then, as I said, if you want to go from the blue thing to something that looks kind of like this blue-black thing, which is cooler looking, but actually keep a guarantee, like you actually know when you're inside. Then you need this kind of cycle detection to kind of numerically prove you have a local contraction mapping. And then you need the Kobe-Korda theorem and so on. But once you do that, there will be red pixels along the boundary because you cannot know where you are through the boundary. Like there's a hard change in behavior. Okay. So I'll just go quickly through this one. So this is like total change of topic. So again, I mostly do AGI safety. And there's some small theoretical part of AGI safety, which you can do kind of complexity theory analogies for. And this is that. I'm not going to just rough motivation. Assume that there's some decent credence on AGI sort of agents appear and they go super intelligent. So you have a lot of machines that can do kind of much more reasoning than humans can do, say either narrowly in some area or like generally at everything. What we'd like to do is be able to turn kind of our human signal, human judgment of what is good, and what we would like the machines to do into some strong supervision signal, some strongly incentivized game that makes them do the right thing. And sort of the theory here is basically like take kind of computational complexity theory, interactive proof theory, and port as much of it as you can into the natural language setting where everything is a mess, without assuming that the ML agents are omnipotent, because they're going to have heuristics and limits and so on. You have to respect those. But I will not say what the result is or what if that requires like more time. So I'll just talk about lean stuff. So one thing is like this is a probabilistic result. This is assuming that you can basically like certify the result of some stochastic computation to a verifier that needs roughly polylog time to do the check, and the computation time is linear. So it's some like you have an n-length computation, n-time computation, and you want the agents to do n polylog n for their work. They're doing the expensive verification, and then the expensive proving. They're the tactics basically, and the humans are doing kind of cheap checking. So it's probabilistic, and this is like half me learning lean force. I wanted to do my own types, but then it turned out to be useful, I think. So we currently have PMF in lean, and we have general measure spaces. But if you use general measure spaces or PMF, and you want to take expectations which are signed, so they can go either way, then you have every time you want to do basically anything, you need some notion of integrability. You need things not to explode to infinity. And if you have a finitely supported distribution, then all of that goes away, and kind of all the naive theorems just kind of apply. So you can do very it's roughly kind of ASOP level, just like apply reasoning. So I didn't know that ASOP when I was doing it. And it's kind of quite nice to express kind of calculations. And then I think so PMF is a monad as well. I did really like writing stuff in monadic syntax. So here, for example, this is like one step of this debate protocol. There are two agents, Alice and Bob, and a verifier, Vera, the standard cryptography names. And so like the first step, sort of let P gets Alice, allow all, whatever. That's kind of Alice proposing a probability. But Alice is some general stochastic computation, so she could do sort of random other stuff. It's not like, and then Bob kind of chooses whether to accept the probability as valid. If he accepts it, you sort of you flip a random coin based on the probability, and then you continue the computation. Otherwise, you sort of call the verifier and then bail out. And this is just very pretty, very like monadic syntax is great. So I was happy with this. Cool. That's what I have. Yeah, again, I didn't run these pictures, so I was just like staring at like lean and thinking about it. It was fun to write that down. So thank you for letting me.
Thanks a lot for the talk. Are there any questions?
One, if you looked at approximate on like halfway through your talk. Yeah, if you don't put the column prop, this by default is going to be entire, which is probably not what you want. True, it should be prop valued, but it's not by default. It doesn't uniform. I should have asked the question.
I don't know why that never came up.
Probably because you never had to unify them, or like you only had one of them.
But I was definitely I was doing a whole bunch of. I guess you're right. You can still prove things about them. You just
Yeah, exactly. Two, the Jordan curve theorem is well, I can tell you that like Geoffrey and I are trying to work on getting the like the group of 6 theorems that are related, like Bottcher, Sperner, KMM, LSP, all of these. All of these. We're trying to get them. And I think you need I think any of these to do the Jordan curve theorem.
cool.
So maybe soon, but I have exams at the end of the week.
Yeah. What does the sort of unbox thing mean when you are?
Yeah. So what it means for it to work is yeah. So basically, like in memory, this is true in most functional programming languages. Everything except for small integers is typed. I forget how Lean does it. And then if you're not, type is boxed, meaning that it is the variable is memory representation is just a pointer to some heap allocated data structure. And so the N64 one does unbox. So there's no memory, there's no extra box around N. It's the same as the representation collapses. So it's the same as U64. But if you have an interval containing 2 floats, which contain 2 effectively UN64s, that's a box containing, it's a pointer to a box containing 2 pointers to 2 boxes. This is like a total mess. So what you'd like is, in these cases where you really want the thing to like flatten out and be fast, you'd like to say, I want this to be totally flat. Like, so you would still have a pointer to an interval, which would then contain just flat fields, like 4 UN64s. And then you have to do a bit of memory copying when you pass it around, but that's cheap. And then it's easier for the compiler to say, okay, now I have a loop. I'm going to unbox around the loop iterations and then make everything totally memory-free. That's nice and fast. So I think this is totally, this is like year 2 of the Lean FRO plans. It's year 2 or later is there a new code generator, and that would then include the unbox for it. And so then this would get quite a bit faster.
Thanks.
Like about the internal arithmetic, so this is in your project, it's not in and because I was like, I also wanted like internal arithmetic or something, and then I was like, okay, it doesn't have it too bad. And second, like I wanted to ask if you could like imagine how one could generalize this for other precisions, right? Because like this
so it turns out that it's actually, the code would get easier if you made it arbitrary precision. Not like strictly easier. You'd have to add a bit of, basically to add precision cutoffs, and the API gets more complicated. But the proofs are much worse because you're working in finite precision, because you have to worry about more kinds of overflow. So if I just did the optimization where I took these structures and I replaced each of these, like the N with I guess both N and S with Z, then I could just like lift the proof into that setting, and everything would like, it would take time. It's like thousands of lines of code.
You need to reimplement all the like functions and so on, right?
But they would all have the similar structure, so it would go through. The other thing you probably want to do to switch from intervals to balls. So the typical way, like if you have two, if you have like high precision, then typically usually your 2 intervals, the 2 bounds in your high precision are very close together. So you're wasting a bunch of memory, about almost 2x memory, if you have basically
You mean like the boxes should be squares?
no, it's like you want to have like one kind of center point, which is high precision, and then a lower precision error around that.
Yeah,
And then you need less less memory for the actual error. So that would be like, that's how R does it. That would be the natural thing to do. That would have to rewrite theorems, but I think it would not be too hard. And that would be more useful for, again, if you want to go to like more precision, you need that. This I kind of did because I wanted to make these pictures. So I also didn't. I hadn't appreciated that unbox was missing. So I think there's more work that the lead compiler has to do to kind of realize the speed you can get out of this kind of thing. There's not that much to get us some horrible software building result.
How much worse is it? Like how, because, so as I understand, you're using lean to actually like compute these values. So yeah, how fast is that? Like
I haven't timed it yet.
but like how does it feel? Like is it
Oh,
really,
it's like
really
orders of magnitude slower.
Okay.
It's kind of, I've only, if I don't use lean to do these renders, I do them with GPUs.
okay.
And
Yes, it's
then
not,
it's
not
like
bad,
embarrassingly different. It would be good to do like an apples to apples like comparison of what.
Like if you compare it like to pixelized Python.
So I think like, for example, like this picture here, if I do it in lean, this is Python, but I did it in lean. Wait, this is Python. But if I did it in lean, it would take at about like 200 by 200 resolution, like a couple seconds. So if you wanted to say, we were talking, Yale and I were talking this earlier, if you wanted to say prove that two curves stay some distance apart, kind of throughout some interval, that would be a perfectly practical tactic to run, I think.
What do you think will happen prospectively? Will people just formalize the Python script and run it on GPUs? Or?
So that is the thing I think is pretty fun to do. If you basically have a roughly straight line program or some like simple DSL domain specific language, and you prove that the thing is correct, and then you just have like a lean, and I think it's like some like syntax which say dispatches, converts the thing into metal or whatever shading language it runs it. That's a fun thing to do. But that it's kind of unsatisfying unless you do really want the CPU analog of that. So if you're going to do interval arithmetic with floats, say, you'd want to have the IEEE float spec formalized and like theorems about that and so on, which is a fair amount of work. I think it exists in, I think, Whole 4. John Harrison, you think did that? And where else? Maybe in Intel.
I think there could be something, or at least I've heard about.
And I know this for import arithmetic in Coq.
Yeah.
Okay, there don't seem to be any questions from the online audience. So I guess I can ask one last question. What do you think will be the role of formal methods in AI safety? Because for proving theorems, there's a nice way to sort of verify that the proof is correct.
Yep.
But in more real-world applications, that becomes more difficult.
So I think there's a couple of different applications. So like the one that I did, like the stochastic doubly-efficient debate thing, that's proving some algorithm correct given a formalized approximation of what you wanted to do. So you can do that, and there's like another example of that is people have done a bunch of work that I don't always think is like, I'm not entirely bought into this being super good, but an example is like causal influence diagrams to show that like, if I train with this method, the ML agent won't do a thing say it won't take advantage of some kind of like do a thing for the wrong reason, like do a thing because it kind of warps its own work function, like, and that's kind of proving the structure of an algorithm is correct. And those you can imagine formalizing. They're kind of standard software formalization problems And you could lift them into kind of the formal land and improve those. I think people do have, the second thing is like, I think if you just formalize, like, I think it helps the world. This is maybe a bit of a side tangent, but it does help the world the more the general space in computer science is not kind of built on this horrible sand foundation where we have nothing is correct. So that if like cryptography is correct and like storage systems are correct and like people, that means people can't like exfiltrate weights when they're not supposed to, and like you can trust that these are like all these kinds of things that helps in terms of MLC as well. And then in terms of actually like formalizing more specific things, I think you can in applications like say your machine in narrow enough applications where your agent is kind of talking to an interface which is simple enough to be formalized, you can directly formalize it. There are people who want to think you can formalize, like say a machine is not trying to persuade a human of something. Formalize against persuasiveness. Those are typically like they imagine there's some sort of hybrid method between where you like have a learned model of what a human does, and you try to like approximate that via some graph you can kind of trace formally, etc. I don't really think those are likely to work, but some people think those are good. I think the main thing I point to are a little bit of this kind of algorithm formalizations of this, but mainly just like there are a bunch of other areas of computer science that like are bad and could be formalized, and those we should at least get right.
Okay, cool. Then thanks again for the talk, and thanks for coming to Cambridge Physics Week.